What's up, everyone? Welcome back to Geospatial Intelligence PH. In this video, I'm going to show you exactly how to generate a slope map from a digital elevation model DEM. Now, if you haven't created your DEM yet, I've got you covered. Check out my previous tutorial on Agisoft Metashape Professional, where I walk you through the entire process. I'll leave a link in the description below. But if you're ready to go, let's dive into the terrain analysis. Let's open ArcGIS Pro. If you're still using the classic ArcMap, don't worry, the tools and steps we're using today are almost identical. Let's head over to the interface. First, let's save our project so we don't lose any progress. Give it a name and choose your folder. It's always a good habit to save early before we start our mapping. Once that's set, we're ready to go. In the catalog pane, let's create a new folder and name it Data or Shapefiles. We need to segregate our rasters and shapefiles so everything is organized and easy to locate when we start importing our datasets. Next, head over to the map ribbon and change your base map to imagery. This gives us a satellite view, making it much easier to identify our location and verify our data against the real-world terrain. Now let's set our coordinate system to WGS 1984 UTM Zone 51N to ensure our slope calculations are accurate. Right-click on Map in the Contents pane and select Properties. Under the Coordinate Systems tab, you can search for 51N to find it quickly. This projected system is essential for measuring real-world distances and angles. Now let's add our digital elevation model. Go to the map ribbon, click Add Data, and browse to the folder where you saved your project files. Locate your DEM. Be sure to select the .tif file for the best results, and click OK to bring it onto your map. For this project, the raw data was captured using a DJI Mavic 3, the LIDAR version, and processed in Agisoft Metashape Professional to generate our orthophoto and DEM. Please take a note, since I exported that data using the WGS 1984 UTM Zone 51N projection. Now let's start the analysis. Go to the command search bar at the very top of the interface and type in contour. This is the fastest way to pull up the tool. In the geoprocessing pane, set your input raster to the DEM we just imported. For the output feature class, click the Browse button and navigate to that shapefiles folder we created at the start. Once the tool finishes, let's rename our layer to Contour 5 meters. For the contour interval, we're going to set this to 5. This is a standard interval often used in geological mapping and terrain analysis to provide a clear, readable representation of the topography. Now that we have our contours, the second step is to convert them into a 3D surface. Go back to the command search at the top and search for Create TIN. This tool will take our vector contour lines and generate a continuous triangular mesh, which is excellent for visualizing the shape of the land. In the Create TIN geoprocessing pane, first choose your output location. Keep in mind that a TIN is its own data type. It's not a shapefile or a raster, so it will appear as a separate folder on your drive. Next, ensure your coordinate system is set to WGS 1984 UTM Zone 51N for the input features. Select your contour 5 meters layer. You can leave the height field, type, and tag field at their default settings. Once that's set, click Run. As you can see on the map, we now have a 3D looking surface. It's important to note that this isn't a raster yet. It's a TIN file. The TIN works by connecting your 5-meter contour lines into a network of triangles, merging the elevation values into a continuous 3D layer. This gives us a much more realistic view of the terrain we captured with the Mavic 3 LiDAR version. Now for step 3, we need to convert this TIN into a smooth raster surface. Head back to the search bar at the top and look for the tool TIN to raster. This process will take our triangular 3D model and turn it into a continuous TIFF file. In the TIN to raster tool, set your output location to the raster folder we organized earlier. For the output data type, Make sure to select Float. Set the method to linear and the sampling distance to observations. We'll leave the sampling value at the default of 250 for now. This will interpolate our tin triangles back into a smooth, high-quality raster surface. Once those settings are ready, go ahead and click Run. And there we have it. We've successfully transformed our 5-meter contours into a brand new, smooth DEM. This raster is now much more refined than our original data because it has been processed through that 3D tin stage. Now, for step 4, we're going to reclassify our new DEM. Search for the Reclassify Spatial Analyst tool at the top. This allows us to group our elevation data into specific classes like low, medium, and high elevation. To find our data, click the folder icon next to Input Raster. This opens your project folder. Double-click on the GeoDatabase icon, the one that looks like a gray cylinder. Inside, you'll find the new raster dataset we just saved. Select it and click OK. Now click on the Classify button. Under Classes, select 6. This will divide our elevation into 6 distinct zones, which is a perfect balance for geological visualization. Once that's set, browse to your raster folder within your project. And click Run. Now for step 5, we need to turn these color-coded zones into actual vector shapes. Go back to the search bar and look for the tool raster to polygon. This converts our 6 elevation classes into a data set of shapes or polygons, which is essential if you need to. Calculate the area of a specific terrain or export this data to CAD or other software. Before we click Run, remember the data type we are creating. This is a shapefile. To keep our project clean, click the folder icon and navigate specifically to the shapefiles folder we created at the start of the tutorial. Once your output path is set to that folder, go ahead and click Run. And there you have it. You have now successfully generated a shapefile-based slope map to see the data behind the colors. As you look through the table, you'll see a column usually labeled grid_code with numbers 1 through 6. These signify the different slope categories we generated. Or our 6th and final step, we need to clean up our data. To fix this, search for the Dissolve tool at the top. Select your slope shapefile as the input, and most importantly, check the box for grid code in the Dissolve fields. This will merge all polygons with the same slope value into a single entry. Once it's finished, you'll have a clean, professional attribute table with exactly 6 rows, 1 for each of our slope classes. Now that our data is dissolved and clean, let's make it look professional. With your layer selected, go to the symbology pane on the right. Change the primary symbology from single symbol to unique values. You'll see your 1 through 6 classes pop up, each with its own color. This is where your map truly comes to life. To make our map technically accurate, we are following the MGB Mines and Geosciences Bureau standards. These classes don't just show steepness, they tell us about the safety and geological stability of the land. I'll help you with your own analysis. I've included a link in the description below to the MGB slope classification sheet. You can download this and use it as your guide to ensure your color coding and terrain categories match the official geological standards used for land assessment and mitigation. This way, your mapping isn't just a visual aid, it's a technically accurate report. Now, we need to add the actual MGB descriptions to our data so it's not just numbers. Open your attribute table for the dissolved shapefile. Click the Add Field button at the top left of the table. We'll name this new field implication and set the data type to text. Don't forget to click Save in the Fields tab at the top. Now that our data is complete and our attributes are labeled with MGB implications, it's time to move from the map view to the layout view. This is where we create the final document you'll actually submit or present. I hope this video helps you a lot in your terrain analysis and project workflows. If you found this useful, please give us a thumbs up and subscribe to the channel for more drone and GIS tutorials.